Right, we're going to continue our discussion on databases in Chapter 2. And this chapter focuses on your data models. You should learn in this chapter about data modeling and why data models are important, about the basic data modeling building blocks, what business rules are and how they influence database design, how the major data models evolved, about emerging alternative data models and the needs they fulfill, and how data models can be classified by their level of abstraction. Alright, database design focuses on how the database structure will be used to store and manage end-user data. Data modeling is the first step in designing a database, and it refers to the process of creating a specific data model for a determined problem domain. A problem domain is a clearly defined area within the real-world environment with a well-defined scope and boundaries that will be systematically addressed. So a data model is a relatively simple representation, usually graphical, of a more complex real-world data structures. In general terms, a model is an abstraction of a more complex real-world object or event. A model's main function is to help you understand the complexities of the real-world environment. Within the database environment, a data model represents data structures and their characteristics, relations, constraints, transformations, and other constructs with the purpose of supporting a specific problem domain. Okay, so your data modeling and your models are used. You have a real-world problem and you model a solution to the problem. Data modeling is an iterative, progressive process. That means you continually add to it. You start with a simple understanding of the problem domain, and as your understanding increases, so does the level of detail of your model. When done properly, the final data model effectively is what they call a blueprint, with all the instructions that you need to build a database that will meet the end user's needs and requirements. The blueprint is a narrative and graphical in nature, meaning that it contains both text descriptions in plain, unambiguous language and clear, useful designs depicting the main data elements. Okay. The importance of data modeling cannot be overstated. Data constitute the most basic information units employed by a system. Applications are created to manage data and help transform data into information, but data are viewed in different ways by different people. Even different managers view data differently. For example, a company president is likely to take a universal view of the data because he or she must be able to tie the company's divisions to a common vision. Okay? A purchasing manager in the same company is likely to have a more restrictive view of the data as it is the company's inventory manager. Alright. Application programmers have yet another view of data, being more concerned with data location, formatting, and specific reporting requirements. The different users and producers of the data and information often reflect the fable of the blind man and the elephant. The blind man who felt the elephant's trunk had quite a different view from the one who felt the elephant's leg or tail. A view of the whole elephant is needed. Okay, so similarly, a house is not a random collection of rooms. To build a house, a person should first have the overall view that is provided by blueprints. Likewise, a sound data environment requires an overall database blueprint based on the appropriate data model. When a good database blueprint is available, it does not matter that an application's programmer's view of the data is different from that of the manager or the end user. If you have a good blueprint for the programmer to follow, what the manager required and what the end user sees and uses it all is a cohesive unit. If they have a bad blueprint, then what the programmer comes up with may not meet the requirements of the manager or the end users. So a good data model is very important when you start creating databases. Alright, the basic building blocks of all data models are entities, attributes, relationships, and constraints. An entity is a person, place, thing, or event about which data will be collected and stored. An entity represents a particular type of object in the real world, which means the entity is distinguishable, and each entity occurrence is unique and distinct. An attribute is a characteristic of the entity, such as the example it gives in your book is a customer entity would be described by attributes such as first name, last name, phone number, address. Attributes are the equivalent of fields in a file system. A relationship describes an association among entities. For example, a relationship exists between customers and agents that can be described as follows. An agent can serve many customers, and each customer may be served by one agent. Data models use three types of relationships: one-to-many, many-to-many, and one-to-one. One-to-many relationships. A painter creates many different paintings, but each is painted by only one painter. Thus, the painter is the one, is related to the paintings, which is the many. Therefore, database designers label the relationship painter paints painting as one-to-many. Many-to-many relationships. An employee may learn many job skills, and each job skill may be learned by many employees. Database designers label the relationship employee learns skills as many-to-many. Okay? One-to-one relationships. A retail company's management structure may require that each of its stores be managed by a single employee. In turn, each store manager who is an employee manages only one store. Therefore, the relationship employee manages store is one-to-one. All right. A constraint is a restriction placed on your data. Constraints are important because they help to ensure data integrity. Things such as an employee's salary must be have the values between 6,000 and 350,000. A student's GPA must be between 0.0 and 4.0. Each class must have one and only one teacher. So that puts constraints on your data. All right. Business rules, brief, precise, and unambiguous description of a policy, procedure, or principle. It enables defining the basic building blocks and describes main and distinguishing characteristics of the data. All right. For a database point of view, the collection of data becomes meaningful only when it reflects properly defined business rules. All right. Again, a business rule is a brief, precise, and unambiguous description of a policy, procedure, or principle within a specific organization. In a sense, business rules are misnamed. They apply to any organization, large or small, a business, a government unit, a religious group, or a research laboratory that stores and uses data to generate information. Business rules derived from a detailed description of an organization's operations help to create and enforce actions within that organization's environment. Properly written business rules are used to define entities, attributes, relationships, and constraints. Anytime you see relationship statements such as an agent can serve many customers and each customer can be served only by one agent, business rules are at work. Okay, so sources of business rules will be your company managers, policymakers, department managers, written documentation on the company, direct interviews with end users. That's the way you will come up with your business rules. So reasons for identifying and documenting your business rules: it helps standardize your company's view of the data. Communication tools between users and designers is it allows the designer to understand the nature, role, scope of data and business processes, develop appropriate relationship participation rules and constraints, and creates an accurate data model for the business when you apply all their business rules. All right, when you translate business rules into data to model your components, nouns translate into entities, verbs translates into relationships among the entities. Relationships are bidirectional. Questions to identify the relationship type. How many instances of B are related to one instance of A, and how many instances of A are related to one instance of B? Okay. Okay, for example, you can assess the relationship between students and classes by asking a couple of questions. In how many classes can one student enroll? Your answer should be many. How many students can enroll in one class? again, it's many. Therefore, the relationship between students and classes is many to many. You will have many opportunities to determine the relationship between entities as you proceed through the book, and soon the process will become second nature. Alright, naming conventions. During the translation of business rules to data model components, you identify entities, attributes, relationships, and constraints. The identification process includes naming the object in a way that makes it unique and distinguishable from other objects in the problem domain. Therefore, it's important to pay special attention to how you name the objects you are discovering. Entity names should be descriptive of the objects in the business environment and use terminology that's familiar to the users. An attribute name should also be descriptive of the data represented by that attribute. It is also a good practice to prefix the name of an attribute with a name or abbreviation of the entity in which it occurs. For example, in the customer entity, the customer's credit limit may be called CUS_credit_limit. The CUS indicates that the attribute is descriptive of the customer entity, while credit limit makes it easy to recognize the data that will be contained in the attribute. The use of a proper naming convention will improve the data model's ability to facilitate communication among the designer, application programmer, and the end user. In fact, a proper naming convention can go a long way toward making your model self-documenting, which means self-documenting means that you can look at it and read everything and know what's going on without having to have a set of documentation to explain what's going on. Alright. Then it starts talking about your different models. The hierarchical model was developed in the 60s to manage large amounts of data for complex manufacturing projects, such as the Apollo rocket that landed on the moon in '69. The model's basic logical structure is represented by an upside-down tree. The hierarchical structure contains levels or segments. A segment is the equivalent of a file system's record type. Within the hierarchy, a higher layer is perceived as the parent of the segment directly beneath it, which is called the child. The hierarchical model depicts a set of one-to-many relationships between a parent and a child. Okay? The network model was created to represent complex data relationships more effectively than the hierarchical model, to improve database performance and to impose a database standard. In the network model, the user perceives the network database as a collection of records in one-to-many relationships. However, unlike the hierarchical model, the network model allows a record to have more than one parent. So, advantages and disadvantages of your hierarchical model. Advantages: it promotes data sharing. Parent-child relationship promotes conceptual simplicity and data integrity. Database security is provided and enforced with a DBMS, and it's efficient with one-to-many relationships. But your disadvantages are: it requires knowledge of physical data stored characteristics. Navigational system requires knowledge of the hierarchical path. Changes in structure require changes in all application programs. Implementation, limitations, no data definitions, and lack of standards. And then your network, the advantages are conceptual simplicity, handles more relationship types, data access is more flexible, data owner membership relationship promotes data integrity, conformance to standards, and includes a data definition language and data manipulation language. Disadvantages is system complexity limits efficiency. Navigational system yields complex implementation, application development, and management. Structural changes require changes in all application programs. And while the network database model is generally not used today, the definitions of standard database concepts that emerged with the network model are still used by modern data models. Alright, such as the schema, which is the conceptual organization of the entire database as viewed by the database administrator. The subschema is the portion of the database seen by the application programs that actually produce the desired information from the data within the database. Data manipulation language, or DML, defines the environment in which data can be managed and is used to work with the data in the database. And then your schema data definition language, or DDL, enables the database administrator to define the schema concepts. Alright, so now let's talk about the relational model. It was introduced in 1970 by a man at IBM. He wrote a landmark paper, A Relational Model of Data for Large Shared Databanks. The relational model represented a major breakthrough for both users and designers. To use an analogy, the relational model produced an automatic transmission database to replace the standard transmission databases that preceded it. Its conceptual simplicity set the stage for genuine database evolution. The relational model's foundation is a mathematical concept known as a relation. To avoid the complexity of abstract mathematical theory, you can think of a relation, sometimes called a table, as a matrix composed of intersecting rows and columns. Each row in a relation is called a tuple. Each column represents an attribute. The relational model also describes a precise set of data manipulation constructs based on advanced mathematical concepts. Alright, so your advantages of your relational model: structural independence is promoted using independent tables. Tabular views improves conceptual simplicity. Ad hoc query capability is based on SQL. It isolates the end user from physical level details and improves implementation and management simplicity. And the disadvantages is it requires substantial hardware and system software overhead. Conceptual simplicity gives untrained people the tools to use a good system poorly, and many may promote informational problems. Okay, so the relational data model is implemented through a very sophisticated relational database management system, or RDBMS. The RDBMS performs the same basic functions provided by the hierarchical and network DBMS systems, in addition to a host of other functions that make the relational data model easier to understand and implement. Arguably, the most important advantage of the RDBMS is the ability to hide the complexities of the relational model from the user. The RDBMS manages all of the physical details while the user sees the relational database as a collection of tables in which data are stored. The user can manipulate and query the data in a way that seems intuitive and logical. And here it shows a relational diagram. You have your agent table and your customer table. You have your primary keys, which are your unique identifiers for each record in your database. You have your agent code in the agent and customer code in customer. But then you have your relationship between the two. Your agent code in agent will have it will be a unique identifier for every record. No record can duplicate that agent code. It's a unique identifier for your agents in your agent table. But then it's a foreign key in your customer table. Your customer code is your primary key, and no customer will have a duplicated customer code. It's your unique identifier. But your agent code, because an agent can serve many customers, your agent code will link back to the agent table to identify that agent, but it can have duplicate entries in your customer table since it's a foreign key just connecting the relationship. Alright, another reason relational database models rise to dominance was their flexible query language. Most relational database software uses structured query language, or SQL, which allows the user to specify what must be done without specifying how. The RDBMS uses SQL to translate user queries into instructions for retrieving the requested data. SQL makes it possible to retrieve data with far less effort than any other database or file environment. From an end-user perspective, any SQL-based relational database application involves three parts: a user interface, a set of tables stored in the database, and the SQL engine. The end-user interface, basically the interface allows the end-user to interact with the data. Each interface is a product of the software vendor's idea of meaningful interaction with the data. A collection of tables stored in the database. In a relational database, all data are perceived to be stored in tables. The tables simply represent the data to the end user in a way that the user can understand. Each table is independent. Rows in different tables are related by common values and common attributes. The SQL engine is largely hidden from the end user. The engine executes all queries or data requests. Keep in mind that the SQL engine is part of the DBMS software. The end user uses SQL to create table structures and to perform data access and table maintenance. The SQL engine processes all user requests largely behind the scenes and without the end user's knowledge. Hence, SQL is said to be a declarative language that tells what must be done but not how. Alright. The entity relationship model is a graphical representation of entities and their relationships in a database structure. The entity relationship diagram uses graphic representations to model database components. Your entity instance or entity occurrence is rows in your relational table, and your connectivity is a term used to label the relationship types. Such as the name of the relationship is usually an active or passive verb. For example, a painter paints many paintings, an employee learns many skills, and an employee manages a store. Okay, that gives you your connectivity. Alright, entity relationship model advantages, visual modeling feels, conceptual simplicity. Visual representation makes it an effective communication tool, is integrated with the dominant relational model. And your disadvantages is limited constraint representation, limited relationship representation, no data manipulation language, and loss of information content occurs when attributes are removed from entities to avoid crowded displays. And then it shows an example there in the figure of an ER model and its notations. There it shows a one-to-many relationship. A painter can paint many paintings. A many-to-many. It shows the different types. It shows the chin notation, crow's foot notation, and UML class diagram notation. Of a one-to-many, a many-to-many, where an employee can learn many skills, and a one-to-one where an employee manages a store. It shows you the different notations of how to map that out. Alright. Increasingly complex real-world problems demonstrated a need for a data model that more closely represented the real world. In the object-oriented data model, both data and their relationships are contained in a single structure known as an object. In turn, the OODM is the basis for the object-oriented database management system. An OODM reflects a very different way to define and use entities. Like the relational model's entity, an object is described by its factual content. But quite unlike an entity, an object includes information about relationships between the facts within the object, as well as information about its relationships with other objects. Therefore, the facts within the object are given greater meaning. Alright. The OO data model is based on the following concepts. An object is an abstraction of a real-world entity. In general terms, an object may be considered equivalent to an ER model's entity. More precisely, an object represents only one occurrence of an entity. Attributes describe the properties of that object. For example, a person's object includes the attributes name, social security number, and date of birth. Objects that share similar characteristics are grouped in classes. A class is a collection of similar objects with shared attributes and behaviors or methods. In a general sense, a class resembles the ER model's entity set. However, a class is different from an entity set in that it contains a set of procedures known as methods. A class's methods represents a real-world action such as finding a select person's name, changing a person's name, or printing a person's address. In other words, methods are the equivalent of procedures in traditional programming languages. In OO terms, methods define an object's behavior. Classes are organized in a class hierarchy. The class hierarchy resembles an upside-down tree in which each class has only one parent. Inheritance is the ability of an object within the class hierarchy to inherit the attributes and methods of the classes above it. And object-oriented data models are typically depicted using UML, or Unified Modeling Language, class diagrams. UML is a language based on OO concepts that describes a set of diagrams and symbols you can use to graphically model a system. UML class diagrams are used to represent data and their relationships within the larger UML object-oriented systems modeling language. The advantages of OO is semantic content is added. Visual representation includes semantic content. Inheritance promotes data integrity. And your disadvantages: slow development of standards caused vendors to supply their own enhancements. Compromise the widely accepted standard. Complex navigational system. Learning curve is steep. High system overhead slows down transactions. And the comparison there of OO, UML, and ER models. Okay. The object representation of the invoice includes all related objects within the same object box. Note that the connectivities 1 to many indicate the relationship of the related objects to the invoice. For example, the one next to customer object indicates that each invoice is related to only one customer, and the many next to the line object indicates that each invoice contains many lines. The UML class diagram uses 3 separate object classes: the customer, the invoice, and the line, and 2 relationships to represent this simple invoicing problem. Note that the relationship connectivities are represented by 1 to 1, 1 star, and 0 to star, and 1 to star symbols, and that the relationships are named in both ends to represent the different roles that the objects play in the relationship. But your customer, you got generates, belongs to, has, and belongs to. You got your different roles there. Alright, and then the ER model also uses 3 separate entities and 2 relationships to represent this simple invoice problem. Alright, object relational data models and XML. Extended relational data models supports OO features and complex data representation. An object relational database management system is based on the extended relational data model and focuses on better data management. And your extensible markup language, XML, it emerged as the de facto standard for the efficient and effective exchange of structured, semi-structured, and unstructured data. Organizations that use XML data soon realized that they needed to manage large amounts of unstructured data such as word processing documents, web pages, emails, and diagrams. To address this need, XML databases emerged to manage unstructured data with a native XML format. So it makes it an efficient and effective exchange of all data types from your unstructured data. Alright, what they call big data aims to find new and better ways to manage large amounts of web and sensor-generated data. Provide high performance and scalability at a reasonable cost. Your characteristics are volume, which refers to the amounts of data being stored; velocity, which refers not only to the speed with which data grows, but also the need to process the data quickly in order to generate information and insight; and variety, which refers to the fact that the data being collected comes in multiple different data formats. Okay, so volume does not allow the usage of conventional structures. Big data is expensive, and OLAP tools provide inconsistent dealing with unstructured data. So that's some problems that they've faced trying to do big data. Big data, new technologies, Hadoop distributed file systems, MapReduce, and NoSQL. Okay, Hadoop is Java-based, open-source, high-speed, fault-tolerant distributed storage and computational framework. Uses low-cost hardware to create clusters of thousands of computer nodes to store and process data. Hadoop originated from Google's work on distributed file systems and parallel processing and is currently supported by the Apache Software Foundation. Hadoop distributed file systems, a highly distributed, fault-tolerant file storage system designed to manage large amounts of data at high speed. In order to achieve high throughput, HDFS uses the write once, read many model. This means that once the data is written, it cannot be modified. Okay, and it uses three types of nodes: a name node that stores all the metadata about the file, a data node that stores fixed size data blocks, and a client node that acts as the interface between the user and the HDFS. MapReduce is an open source application programming interface that provides fast data analytics services. MapReduce distributes the processing of the data among thousands of nodes in parallel. MapReduce works with structured and non-structured data. The MapReduce framework provides two main functions: map and reduce. In general terms, the map function takes a job and divides it into smaller units of work. The reduce function collects all the output results generated from the nodes and integrates them into a single result set. NoSQL is a large-scale distributed database system that stores structured and unstructured data in efficient ways. NoSQL databases are discussed in more detail in the next section in your book. Every time you search for a product on Amazon, send messages to friends on Facebook, watch a video on YouTube, or search for directions in Google Maps, you're using a NoSQL database. As with any new technology, the term NoSQL can be loosely applied to many different types of technologies. However, this chapter uses NoSQL to refer to a new generation of databases that address the specific challenges of the big data era and have the following general characteristics. They are not based on the relational model in SQL, hence the name NoSQL. They support distributed database architectures that provide high scalability, high availability, and fault tolerance. They support very large amounts of sparse data, and they are geared toward performance rather than transaction consistency. NoSQL databases are not based on the relational model. In fact, there is no standard NoSQL data model. To the contrary, many different data models are grouped under the NoSQL umbrella, from document databases to graph stores, column stores, and key value stores. The key value data model is based on a structure composed of two data elements, a key and a value, in which every key has a corresponding value or set of values. The key value data model is also referred to as the attribute value or associative data model. Okay, advantages for NoSQL: high scalability, availability, and fault tolerance. Uses low-cost commodity hardware, supports big data. Key value data model improves storage efficiency. Disadvantages: complex programming is required. There is no relationship support. There is no transaction integrity support. And in terms of data consistency, it provides an eventually consistent model. Simple key value representation here. In the relational model shown, each row represents one entity instance, each column represents one attribute of the entity, and the values in a column are of the same data. In the key value model, each row represents one attribute value of one entity instance. The key column could represent an entity's attribute. The value in the value column could be any data type, and therefore it is generally assigned a long string data type. So the evolution of the DBMS has always been driven by the search for new ways of modeling and managing increasingly complex real-world data. So for a quick summary, your hierarchical and network back in the 60s, difficult to represent many relationships in the hierarchical, structural level dependency, no ad hoc queries, record at a time access path predefined for navigational access. In the 70s, you had the relational came out, conceptual simplicity, structural independence, provides ad hoc queries with SQL and set-oriented access. In 76, the entity relationship was introduced, and it's easy to understand, has more semantics, limited to conceptual modeling, no implementation component. 78 through 90, you had your semantics with object-oriented and extended relational. More semantics and data models. Support for complex objects, inheritance, and class hierarchy were introduced. More behavior, unstructured data was supported by XML. Okay. And then big data with no SQL addresses big data problem, less semantics and data modeling based on schema, less key value data models. Okay, so we don't have a schema, we use the key and value data model. Best suited for large, sparse data stores. Data model basic terminology comparisons between the different models and groups there. I'll let you guys look over that. If you have any questions on that, you can let me know. There's also a table in your book on page 55 that you might want to take a look at that's advantages and disadvantages of the various data models and compares your data models, which that was introduced in different places in the slides, but it's brought together in a single table there. Data abstraction. All right. So if we talk about the external model, the external model is the end user's view of the data environment. The term end users refers to people who use the application programs to manipulate the data and generate information. Because data are being modeled, ER diagrams will be used to represent the external views. A specific representation of an external view is known as an external schema. And here it shows that a professor may teach many classes, and each class is taught by only one professor, so there is a one-to-many relationship between the professor and the class. A class may enroll many students, and each student may enroll many classes, thus creating a many-to-many relationship between the student and class. Each course may generate many classes, but each class references a single course. For example, there may be several classes or sections of a database course that have a course code of CIS117. One of those classes might be offered on Monday, Wednesday, and Friday, 8 a.m. to 8:50 a.m., and another might be offered on Monday, Wednesday, Friday from 1 p.m. to 1:50 p.m., while a third might be offered on Thursdays from 6 p.m. to 8:40 p.m. Yet all three classes have the course code CIS117. Finally, a class requires one room, but a room may be scheduled for many classes. That is, each classroom may be used for several classes, one at 9, one at 11, and one at 1. In other words, there is a one-to-many relationship between the room and the class. Alright, I'm sorry for the interruption. We finished up the discussion of this slide. Alright, let's look at conceptual model. It represents a global view of the entire database of the entire organization. A conceptual schema is a basis for the identification and high-level description of the main data objects, avoiding any database model-specific details. It has a macro-level view of the data environment, is software and hardware independent. It has a logical design task of creating a conceptual data model. Software independence means that the model does not depend on a DBMS software used to implement the model, and hardware independence means that the model does not depend on the hardware used in the implementation of the model. And generally, the term logical design refers to the task of creating a conceptual data model that could be implemented in any DBMS. And then it shows there an example of a conceptual model for a tiny college. The internal model is the representation of the database as seen by the DBMS. In other words, the internal model requires the designer to match the conceptual model's characteristics and constraints to those of the selected implementation model. An internal schema depicts a specific representation of an internal model using the database constructs supported by the chosen database. It is software dependent and hardware independent. It's not dependent on a specific set of hardware, but it is dependent upon the DBMS that's chosen. If you can change the internal model without affecting the conceptual model, you have logical independence. However, the internal model is still hardware independent because it is unaffected by the type of computer on which the software is installed. And here it shows your model, again for a tiny college. It shows the conceptual model there to the side, and then the internal model. You would create your professor table and put your attributes in, your entities and your attributes in, your class table, your room table, and your course table. Alright, the physical model operates as the lowest level of abstraction, describing the way data are saved on storage media such as magnetic, solid state, or optical. The physical model requires the definition of both the physical storage devices and the physical access methods required to reach the data within those storage devices, making it both software and hardware dependent. The storage structures used are dependent on the DBMS software and on the operating system, and on the type of storage devices the computer can handle. The precision required in the physical model's definition demands that database designers have a detailed knowledge of the hardware and software that is going to be used to implement the database. Early data models force the database designer to take the details of physical models' data storage requirements into account. However, the now dominant relation model is aimed largely at the logical level rather than the physical. Therefore, it does not require the physical level details common to its predecessors. When you can change the physical model without affecting the internal model, you have physical independence. Therefore, a change in storage devices or methods, and even a change in the operating system, will not affect the internal model. So here it shows levels of data abstraction. So with external, degrees of abstraction from physical to external. Physical is low, internal is a little better, conceptual is better, and external has a high degree of abstraction. External focuses on your end users, conceptuals, global view of the data. Internal, specific database model, and physical storage and access methods. External is independent of hardware and software, so is conceptual. Internal is independent of hardware, and physical is independent of neither. It is both hardware and software dependent. Alright, that wraps up our lecture of on Chapter 2 on your data models. If you have any questions, please let me know. Otherwise, that will wrap up our discussion on data models.